We'll finish off section 3 with a famous classical probability problem that you may well have come across before. It's normally called the birthday problem. And it's the problem where we have a bunch of students in a class together and we wonder if any of them share a birthday. And so we're going to look at that problem here. So this is the problem. There are k equals 23 students in a class. What's the probability at least 2 of them share a birthday? Now, just to be clear, in this question we're going to assume that all 365 days of the year are equally likely and we're not going to worry about leap years. So we do have a classical probability problem of equally likely outcomes. So, same thing we always do. What's the sample space? What's the event? Sample space omega is the possible set, the set of possible birthdays, birthdays for the k students. And obviously, each student has 365 choices for what their birthday could be. So that's 365 to the k, just to the normal k, because it's at least possible that they will share birthdays. So 365 to the k for the set of possible birthdays. I'm going to avoid setting k equals 23 until I have to, if I can. So there are 365 to the k possible birthdays. What about our event A, the event that at least 2 students share a birthday? Well, one thing you might notice here is that this is one of these at least questions, right? And we mentioned before that when you have an at least question, it's often a good idea to use the complementary event instead, because that can sometimes be easier to work with. So because we've got an at least question, maybe we should think about a complement. So if A is the event that at least 2 students share the same birthday, a complement is the event that there isn't a pair of students that share a birthday. Right, this is all students have different birthdays. Right, because if there aren't 2 students sharing a birthday, that must mean that every single student has a different birthday from each other. And so can we count the number of outcomes in a complement? Well, yes, right. If the first student has 365 possibilities for their birthday, the second student, if they want to avoid having the same birthday, only has 364 choices. And if the third student wants to avoid both the first person's birthday and the second person's birthday, they only have 363 choices. And so on. Everyone needs to avoid the birthdays of the people ahead of them in the line. And so this is our old friend, the falling factorial, right? This is 365 to the k, but this time underlined. So omega, the possible birthdays, was just your normal 365 to the k, sampling with replacement. But if we want all the students to avoid each other's birthdays, we have 365 to the k underlined. Our friend, the falling factorial, because they have to be chosen without replacement because we can't have the same birthday twice. So if we put this all together, what's the probability of A, the probability that at least 2 students share a birthday? Well, we know that's 1 minus probability of A complement. We know because of classical probability, that's the number of outcomes in A complement over the number of outcomes in omega. So that's 1 minus 365 to the k falling factorial over 365. Or, if you prefer to write it out longhand, it's 1 minus 365, 364, etc. 365 minus k plus 1. And sorry, I missed out the power k there. 365 to the k on the bottom, and you could put all the 365 to the k's on the bottom out separately if you like. So that's the number. I typed this into R earlier. You can see the command I used in the notes, and I got the answer 0.50 7, so just above 50%, nearer 51%. So it's more likely than average, more likely than 50-50 that at least 2 students share a birthday. Now, I wouldn't be surprised if you've seen that problem before, but if you haven't seen that problem before, that often surprises people that just 23 students can have more than 50% chance of sharing a birthday. So this is when k equals 23. But the key is, it's kind of pairs of birthdays that are possible matches, right? And the number of pairs of birthdays amongst the 23 students is, of course, 23 choose 2, right? Pick 2 students out of the 23. And that's 253. So in a way, you've had 253 birthday pairs which had a chance to match. And so although 23 sounds like a small number of students, if you think of it in terms of pairs of students, of which there are 253, then it's not surprising that one of those 253 happens to be a birthday match, because each of them have a 1 in 365 chance. So that's a classical probability problem known as the birthday problem.